Good morning, everyone. I forgot about something. Today is Engineering Expo, right? Thursday. Okay, Thursday. All right. So it's just Thursday, or it's Thursday and Friday, Wednesday and Thursday? Just Thursday. Okay. So how many of you are not going to be here on Thursday? Okay, I see almost half. So I'll see what we can do in order to catch up with that, and if we have a lecture or not. Probably we'll have a lecture, but then you can watch the lecture later on. But I'll let you know, okay? All right, so let's continue with what we were seeing about pore pressure. First of all, the first thing that we did in geomechanics was to extend our knowledge in order to calculate the total vertical stress. And that's a very important value that we're going to use a lot in this class for geomechanical calculations. The second thing that we did was to calculate pore pressure. And we extended this pore pressure to some cases in which the pore pressure is not hydrostatic. And I have here one example of that. This is a figure in which you see pore pressure in blue, and here in red you have the fracture gradient. And one of the main objectives of this class is going to be to calculate the fracture gradient. But for now, let's just assume this is the fracture gradient, and vertical stress would be somewhere over here in this line, and like a line somewhere over there. But it's not drawn in this case. Let me see if in the previous one is drawn. No, in this one it's not. Okay, so let me ask you something. Let's see if you remember something from last class. Would you say that in this particular reservoir, which is a real example, do you have overpressure at some point or not? And if yes, at what depth? At what depth does overpressure start? Around 8,000 feet, right? So you can see that around 8,000 feet, somewhere over here, the pressure changes, and the trend will be a line that will continue like this. But at 8,000 feet of depth, this pore pressure starts to increase. And that's something that we said it's called overpressure, and in general it's non-hydrostatic pore pressure. But what's happening here at around 13,000 feet of depth, 13,000, let's say 400 or so? What happened to pore pressure there? It's a lot lower than what is in adjacent formations, right? So what do you think might be going on in there?
It went back to hydrostatic pressure.
What?
It went back to hydrostatic. Maybe there's a fraction that connected the...
Okay, that could be. It looks like it's getting closer to hydrostatic, but it might or it might not. There is something else going on there. What? I didn't get it. No. Well, I'll tell you part of the answer. This overpressure that we see over here, it's caused by natural causes. But sometimes we can also have alterations of pore pressure caused by ourselves. Also sometimes by nature, but what you see over here, it was caused by somebody else that did something. What could that be? If this is a reservoir formation at this depth, you could have had there like an oil reservoir that at some time it was depleted, and that's why the pressure is so low right now. If there is no good pressure drive, if there is no good pressure communication, the pressure is just going to stay low for a long time. It's going to slowly ramp up Probably, as you were saying, it might go to hydrostatic, or it might go to a value higher than hydrostatic if the water drive is coming from overpressure formations. But we have at this point an example in which the pressure is not hydrostatic and it's not overpressure, but it's something else. This is caused by depletion, and it could be here, or it could be there, or it could be there. It depends on how hard the depletion was. And this is the last topic that I wanted to briefly discuss over here, and this is the under pressure caused by depletion. And this is a serious problem, because when this happens, and let me, I have the explanation in this example over here, but there are too many lines in there. This one I found that it's a lot easier to look at. The problem over here is that when your pore pressure goes down at a given depth, also the fracture gradient is going to go down, and we're going to see why. And when the fracture gradient goes down very quickly, that's very problematic for drilling, because if we look now at this in equivalent weights for drilling, and we're going to see this later on in detail, guys, don't worry about this, you will see that the available window that we have for the mud weight is this one, and then when we have a deplete formation, the fracture gradient is going to get a lot lower than what it used to be, and that's going to narrow down the drilling mud window quite a bit. And that's going to be very important, and that's going to be something that we're going to calculate later on. But this under pressure then is caused by depletion. And this sometimes is a serious problem, because, for example, when you go to very developed fields like in West Texas, where there has been a lot of depletion in the past of conventional reservoirs, now if you're going to go to the source rocks, you have to go through all those formations that were already depleted. And if they have these problems of low fracture gradient, then you're going to have to face that when you drill your wells. All right, so with that, we end the topic of non-hydrostatic pore pressure. I hope you guys start to work on the homework. I don't know if you have any question about the special. I think we work more or less on everything except problem number 3, that you need to use this shale porosity over here in order to calculate pore pressure. And as I was telling you, there is an example problem in the notes that you should use. It's more or less straightforward. So, did you start working on this or not? Yeah? Okay. Well, if you haven't, again, just check the problem in the notes, and you will see this is not complicated. All right. We'll go now to the last subsection in this chapter, which is horizontal stress. All right, so we have talked about vertical stress, we talked about pore pressure, but there is something else that we need to calculate, and which is super important in geomechanics, and that's horizontal stress. What is the difference between a solid and a fluid? Can anyone tell me that? What did you learn in physics? Yes? The fluid takes the shape of its container, and what about if, instead of talking about the fluid, how could you rephrase that for a solid? Maintain its shape, and the solid will maintain its shape when it has a stress on it. For example, if I have something similar to a box, like this charger over here, and I apply a stress on the bottom and the top, it's not going to change shape, right? because it's a solid, it can maintain its shape. You can see also this a little bit differently and say that a solid can support shear stresses or can support stresses in different directions which are not the same. Because for example now, to this box I apply a force bottom and top, but I'm not applying anything on the sides. The solid can maintain that difference of stress because it's a solid. And we're going to see that part of that property of the solid is something that we're going to call the shear strength. And we're going to see that later on. But in a solid, in a rock, because it's a solid and because it has a shear strength, we're going to have stresses that are different in different directions. And we already talked about vertical stress, but because of the property of the solid maintaining stresses in different directions, there are also going to be stresses which are perpendicular to this vertical stress, which are going to be different in magnitude to the vertical stress in general. And because this is a three-dimensional solid, we're going to see that we're going to have three orthogonal stresses that in general those are going to be different in magnitude. And for this simplified case, this is going to be the vertical stress, what we are going to call the horizontal minimum stress and the horizontal maximum stress. And this makes things a little bit more complicated because now in geomechanics we need one pore pressure, three stresses, and not only that, we need the values of the three stresses, but also we need to know the direction of those horizontal stresses. The direction of those horizontal stresses is going to vary from place to place. And we're going to see that also that's very important for geomechanics. Don't worry about this matrix right now. We'll talk about that later on. What I want you to remember from now is that at any point in the subsurface, we're going to have three stresses, three directions associated to those stresses, and one pore pressure. So we have 7 unknowns that we need to figure out before we think about a particular problem. All right, so let's take for granted now that these horizontal stresses are out there, and what we'd like to know is why they vary from place to place. And they're going to vary in magnitude and in direction. And here you have one example that can help you see the effect of horizontal stresses and what is the source of those changes of horizontal stresses. In this example, we see a map here of the west coast, and here you have the San Andreas Fault. And next to that San Andreas Fault, if you go with Google Map or with some picture from an airplane, you will see something like this, in which you have two parts of the aircraft that are moving with respect to each other and kind of like shearing with respect to each other. And that's caused because the horizontal stresses are combined in a way that they push very hard in this direction and not that much. Let me rephrase that. They push very hard, more or less, in direction north-south, but not that much in direction east-west. So the result is that these two plates, they move like that. But that's because of the local orientation of the horizontal stresses and also the relative magnitude. And I'll explain a little bit more about this, so it makes more sense in a bit. I wanted to show you another example over here, which is an example of a road. So here you see more clearly how, because of faults at this particular location and tectonic plates, which is a force behind, you have this offset in a road. At some point, of course, it was straight, but because of the horizontal stress, and apparently there was an earthquake here. This is also close to San Andreas Fault. This moved like that. And that this is caused by the horizontal stresses. But in general, the variation of horizontal stresses is linked to the tectonic plates. I'm sure you remember this from your geology class about the tectonic plates. For example, which tectonic plate is this one? Here on the far left of the map. The Pacific plate, right? What about this one over here? North American plate, right? Well, here in the San Andreas Fault, you have the Pacific plate, the North American plate, and this other small plate. I don't remember the name. Anyone remembers that? This one, it's over here. It doesn't matter, okay? But those three, I mean, it doesn't matter the name, but it matters that they, at this point, they all kind of like get together, and the way the tectonic plates move is what gives origin to horizontal stresses. And you know that you can make a road trip if you go to California and go the same way that you may pass, let's say, from the US to Mexico, or the US to Canada. You can drive over a plate. You can go from the North American plate to the Pacific plate. So just, just going from one side to the other. But the story is that, the tectonic plates are going to define these horizontal stresses. Do you guys remember the three types of tectonic plate boundaries? So, convergent, divergent, and transform, which is closer, if we'll take a look at it in mechanical terms, it's more like a shear. And it depends where you're located, how those tectonic plate movements are going to change the stresses. For example, if you are closer to a region in which, like somewhere over here, you have a convergent plate boundary, you will expect your horizontal stresses to be quite higher than if you are in a divergent boundary. Also in this location, and also you can see the arrows over here. Let me zoom in a little bit more. In which direction you would expect your maximum horizontal stress to be? If you had these convergent plates over here it's the Nazca plate and the South American plate. They are both converging. Nazca plate going west to east, South American plate going east to west. So in which direction would you expect your maximum horizontal stress? If these are colliding like that, very likely this maximum horizontal stress is going to be in direction east-west too. And that's what you see with these arrows. The direction of these arrows over here tells you in this map what is the orientation of the maximum horizontal stress. And again, as you may expect, when the plates, they converge in this direction, the horizontal stress is going to be more or less the same in the direction in which the plates, they move. Like for example over here, or if you go somewhere here to Asia, in the Himalayas here, you will see how the direction of the horizontal stress is aligned with the direction in which the tectonic plates are moving. And these stresses are not going to be only at the boundaries, but they are also going to propagate into the tectonic plates. And that's what causes mountains, what causes faults. And when you go inside tectonic plate, it actually may get a a little bit different to what you see near the boundaries. And that's what we're going to see in a little bit. But remember, one of the main drivers of the orientation and magnitude of horizontal stress is the tectonic plate movement. So according to the location in which you are, you can more or less tell what's going on. But if you want to know for sure the magnitude of horizontal stress and direction, you're going to have to do some tests in the field. Okay. Before you get to do some tests, you can also more or less interpret from some geological indicators what is the direction of stress. For example, as we were saying, if you have an anticline which is going with an axis in direction north-south, like here this is north, this is south. You have an anticline which is like this, going with the axis in this direction. You may expect that the horizontal stress, the maximum is coming, or the causal is that anticline is coming in this direction because it made this fault, right? If you had the anticline going east-west, you will expect the maximum horizontal stress, in this case, to be north-south. So looking at some indicators on the surface can tell you more or less what is the orientation of the horizontal stress that caused that feature. Another type of indicator is this type of formation, which is called a dike, a magmatic dike. And these magmatic dikes are actually natural hydraulic fractures. When magma gets pressurized at a value which is, let me say for now, just high enough, it may open the earth the same as a hydraulic fracture would do, and that magma is going to flow through the fracture. Once it solidifies, it will leave something like what you see over here, which is a cross-section of a dike. And in this case, actually solidifying, it has propped this fracture, so that's why you can see it. And sometimes if it goes to surface, you can see it on surface too. In this case, you see this magmatic dike because it has a much more weathering resistance to the ambient conditions than the surrounding rock. So this magmatic dike is going to be a lot harder to weather, and that's why you can see here. If you travel to New Mexico, this one is in New Mexico close to a town called Shiprock. So if you go around there and you want to take a look at these dikes, that's where you're going to find them. All right, so since we're here, we talked, now you know that we have a pore pressure, we have a vertical stress, and we have two horizontal stresses, right? All right, so let's look at this dike over here. What do you think was the pressure needed for that dike to open up the ground? Yes. And what is a fracture pressure? Yeah, but what? What specifically? So let me help you a little bit with this. I'm going to, let me move this over here. So we're talking about this dike. So I'll give you time to think about that. But remember that what we have learned so far, and then now we know that in any point in the ground we're going to have three stresses and one pore pressure. and this is going to be a porous rock, and inside that porous rock we have a pore pressure. So let's rewind a little bit. If you go into a reservoir and you want to push the fluid in a reservoir with another fluid, your pressure has to be higher than the pore pressure of the formation. That will allow you to push the fluid in the rock. Probably a little bit higher, right? Because you have some viscous losses, a pressure gradient, but the minimum pressure you're going to need, for sure, is going to be the pore pressure. All right, my question now is, what is the pressure that you will need on inside a fracture in order to split the ground in two and make this dike propagate? Yes?
Is it H1?
Yes, but there are some assumptions there. So, but I like to hear how you came to this conclusion. Can you tell me?
It's like the minimum pressure you need to cause a fracture.
Yes, but there is one assumption there. So you remember that I was telling you that the vertical stress, if you were to put a hydraulic jack and you will pressurize that jack, you will need a pressure in the hydraulic jack which is equal to the vertical stress in order to lift the ground up, right? Well, in this particular location, for the way in which this dike is propagating, and is propagating opening against the rock as a vertical fracture and pushing horizontally, what you're saying is correct. The minimum pressure that required to open that fracture is going to be the minimum principal stress. But that's going to be just in the condition in which this inequality holds, which means that the minimum principal stress is the horizontal stress. And sometimes that might not be the case. For example, in this location where apparently that dike is not propagating vertically but is propagating horizontally, we could have a reversal of stresses, and in this condition the minimum principal stress is going to be the vertical stress. So now the minimum pressure needed to open a hydraulic fracture now is going to be the vertical stress. And we're going to see why we have these variations and how we can calculate those. But I hope that from this natural example also you can see that this is going to be very important for us for hydraulic fracturing. For example, if you were to do a hydraulic fracture and now it's not a magmatic dike anymore, but it's actually a hydraulic fracture, and your fracture propagates vertically like this and then gets to a formation and start propagating horizontally, this is what is called a T fracture. And that's going to be caused by the variations of horizontal stress with depth. Well, if you want to really know, what is this value of the horizontal stresses, then you have to measure it. And that's what we're going to do later on, not in much detail right now, because we have to learn many other things in order to get there. But I'm just going to tell you very quickly what this is about. You can run hydraulic fracturing tests in which you measure how the pressure, what is the maximum pressure in a wellbore, how that decreases, in order to tell what is the value of the fracture gradient and what is the value of the minimum principal stress. Later, if you go to this wellbore, you can run a formation imaging tool like this one, like this one, or like that one over there, that you have an image of the well, and you can see in which in which orientation the fracture formed. So you can say in the subsurface in which direction your fracture went. And that's going to tell you what is the orientation of the stress. Okay, and I wanted to talk about that specifically today. So let me just hang a little bit in there about what is going to be the orientation of a hydraulic fracture. Hopefully by now you more or less have an idea. So we answered what will be the minimum pressure for the hydraulic fracture. We also answered what will be the orientation when it changes from vertical to horizontal. But I like that we answer later if it's a vertical fracture, in which direction it's going to be, right? If it's going to be a plane in direction south, north-south, or east-west, or at any angle. We're going to answer that in a little bit. All right. Any questions so far? No? Okay. Then we'll continue. We're going to see some other methods too. For example, when you drill a wellbore and you take a look at where specific failure around the wellbore forms, that's also going to help us to see what is the direction of the minimum principal stress. But we'll see that later on, so don't worry. What I'd like to discuss now is something which is called stress regimes. So we said that we have three stresses: the vertical stress, the maximum horizontal stress, and the minimum horizontal stress. Let me skip this map for a bit. I don't know if I have a table of that here, but if not, I'll make it. Apparently I don't have it. Okay, so I'll have to do it. Okay. So we have three stresses, and in general those we're going to refer to as S1, S2, and S3, where this is going to be what we call the least total principal stress. And S1 is going to be the largest, and so this is going to hold. This is going to be equal or larger. And because we have three types of stresses, and vertical, maximum horizontal, and minimum horizontal, we are also going to have three combinations of those, how those order. And when the maximum stress is vertical and the minimum stress is horizontal, and we have this type of combination, we're going to call that a normal stress environment or a normal stress regime. The name of that normal, it comes from the analysis of faults. And we're not going to get in detail about that right now, but just let me draw some schematics that are going to help you see what's going on. In a normal state of stress, your maximum stress is going to be SB, the intermediate one is going to be SH max, and the minimum is going to be SH min, and you're going to expect to have a fault that forms more or less like this, where this side goes down and this side goes up. Let's go to the next one. Let's go to the complete opposite, which is the reverse. In the reverse faulting regime, the maximum principal stress is horizontal, the minimum is vertical, and the intermediate is the minimum principal stress. And under this condition, now we will have, as we were saying, the maximum on horizontal direction, the minimum in vertical, and the intermediate to be horizontal as well. And you would expect to have a fault that forms a lot less steep than the previous one, and this part is going to go up and this part is going to go down. So just for you a little bit to remember the names, the first one is called normal because that's a way that you would expect a fault to move in the most common situations. That what is above the fault, that's called the hanging wall, that will move down with respect to what is below the fault, which is called the footwall. And that's what is called a normal fault movement. When the opposite happens, the hanging wall moves up, which is contrary to gravity, right? That's what is called reverse, because it's the opposite of normal. And also some other times this is called a thrust faulting regime, and we're going to see that also in a little bit. And we have one more to talk about and to define, and that's going to be a case which is called strike slip. And now the maximum horizontal stress is horizontal, the minimum is horizontal too, and the intermediate is vertical. And when we have this condition, you would expect a fault to happen similarly to what we saw before for the San Andreas fault. The intermediate is going to be vertical, the maximum is going to be horizontal, and the minimum is going to be horizontal. So what is really going to make the rock fail is the maximum and the minimum. And when you have that, you will expect a fault to form like this, like a vertical plane, and in this case this side will move backwards and this side will move to the front. And these three types are what are called the stress regimes, and they depend on the relative magnitude of each of those horizontal and vertical stresses. Let's see how this varies in the US, and then we'll come back to an application. Here you have a map that shows what is the stress environment and what is the orientation of the maximum horizontal stress in the lower 48 United States. So you can see, for example, that in red we have normal, in white we have strike slip, and in blue we have reverse or thrust faulting regime. So which stress regime do we have in Texas mostly? Normal, right? So if you do a hydraulic fracturing job in Texas, most of Texas, what will be the orientation of those hydraulic fractures? Would you expect them to be vertical or to be horizontal like a pancake? Vertical, right? But don't be misled, because you may be in some other places, like probably you may have some application here in the East Coast, and that's not going to happen. That's going to be the opposite. If you do hydraulic fracture, it's going to be horizontal. The same as you go in some parts of the West Coast, and you know, have you guys gone to Santa Barbara around there? If you go to the beach, you will see that the oil rigs are not far from there. So you also do a hydraulic fracturing job over there, you will expect some of your hydraulic fractures not to be vertical but to be horizontal. So that depends on where you are. On most of the petroleum producing places in the US, it is normal. But remember that it's not going to be the same everywhere. You may be working in Texas and then you are moved to work to Pennsylvania or somewhere else. The same recipe for hydraulic fracturing that you use in Eagle Ford is not going to work for the Marcellus. You have to see what's going on over there. All right, and this, as we said before, this is closely related to the tectonic plates, right? So you see that here near the West Coast, it changes quite a bit, and that's because of we're very close to the plate boundaries. All right, there is something else I want you to notice here, and it's the direction of those arrows. The direction of the arrows, similar to what we were seeing before, is telling you what is the direction of the maximum horizontal stress. So let me draw something here to make it a little bit easier to understand. We're going to do this mathematically later on. This is something which is called a principal stress, and you can calculate it with a mathematical function which is called an eigenvalue, but let's not get in that right now. I just want you to understand what this plot is. And for example, if you had, let's just imagine a plate with a hole, and you apply stresses only in one direction. If you were to draw what is the direction of the maximum stress in this particular location, close, far from the cavity, is going to be like this. This is telling you what is the orientation of the maximum stress. Same over here. But as you get closer to the cavity, this will start to bend, because in this particular example, stresses cannot go through a cavity, and so those stresses will bend. Probably far from the cavity, these are going to stay the same, but as you get closer, those start to deviate, and you will see something like this. So the direction of those lines over there are telling you the orientation of the maximum horizontal stress. So we know, for example, that in somewhere around here the Eagle Ford formation, so Austin right somewhere over here, and the Eagle Ford somewhere over there. We know that the horizontal stress is pushing in direction more or less east-west, a little bit, I would say, northwest-west. So a little bit to the north, right? If you go to the Permian Basin, somewhere over here, you will also see that closer to the south, this is also going direction east-west. All right. So here is the question. If you were to drill a horizontal wellbore here in the Permian Basin to make several hydraulic fractures, well, first of all, let's say, what would be the direction of hydraulic fracture you would expect here in the Permian Basin? Vertical, right? And we're going to get into more detail right now. So if the maximum horizontal stress pushing east-west, what would be the direction of a horizontal wellbore in order to make several hydraulic fractures in the same wellbore? North-south. Why north-south?
Because when you make the fractures, it'll open up against the minimum horizontal stress.
Very well. Yeah, that's the reason. So let's try to draw that. All right. So let's see if I'm good enough to draw the state of Texas. Something like this, right? Not bad, right? Okay. So we are saying in this case that the horizontal stress, and let's just assume, just for simplicity, is in direction east-west. So the north is here. And the question was what direction we will drill a horizontal wellbore so that we have multiple hydraulic fractures. So in order to answer that, we need to know what is the orientation of the minimum principal stress. We already answered before that in this particular location, let me change color. In this particular location, we have a normal faulting stress regime, which means that the minimum principal stress is horizontal and the maximum principal stress is vertical. So we already know that those fractures are going to be vertical. And they are going to be perpendicular to the minimum principal stress. If we know what is the direction of the maximum principal stress, we also automatically know what is the direction of the minimum principal stress, because those are going to be perpendicular to each other. That's a property of these principal stresses that also we're going to see later on how we get that from mathematics. But those are going to be perpendicular. So if we know one, we know the other. And the last thing is that you remember I was telling you that the pressure needed to open a hydraulic fracture in a normal faulting place at least will have to be the minimum horizontal total stress. Well, that's the magnitude of the pressure, but also that fracture is going to open up, pushing against the minimum principal stress. So if this is a fracture over here, let me draw that again, that was not good enough. If this is a fracture, this is going to open up with a pressure which is larger than the minimum principal stress, but it's doing work against that. The fracture is pushing against that minimum principal stress. And if we have several of these, let me draw that again. That means that we will need a wellbore. Wait, this drawing in the tablet is something new to me. So just give me a little bit more of time. So this is going to be the horizontal wellbore. That we will need in this particular location to open these fractures perpendicular to the minimum principal stress. So I hope that this kind of makes sense to you, but I have one more example in order to show that. So I brought here a balloon, and I'm going to ask an easy question. What is going to be the shape of the balloon if I inflate the balloon? It's spherical, right? More or less. There are many reasons for this. One of them is the material of the balloon, but the most important one that you should remember is the conditions outside, right? So what are the conditions that we have right here? Yes?
Equal pressure right now.
Equal pressure, right? And what is the value of pressure?
1
How much?
atm.
One atmosphere, right? So the pressure I have to use in order to inflate this balloon is at least 1 atmosphere plus what is needed in order to stretch this this balloon, and that's the pressure that I would need. And it has a more or less spherical shape because the pressure is the same in all directions. Well, now imagine that I don't have that box, but imagine that we put this balloon in a box with the walls that do not move in any direction. If I inflate the balloon, at some point, the balloon is going to take the shape of the box, right? And now let me change a little bit the conditions. This box is going to have a stress on the walls that on the bottom and top wall we have a vertical stress that, let's say, is 10 atmospheres. On the walls facing east-west we have a stress which is 5 atmospheres. And on the walls north and south we have a stress of 2 atmospheres. Okay? If I keep on inflating the balloon, which walls are going to be moving? The north-south, top-bottom, or east-west? So remember, 10 atmospheres, 5, 2. You should remember that nature is always lazy, always trying to do the minimal amount of work. So if I were to continue inflating the balloon, why would I push against 10 atmospheres or against 5 atmospheres when I can push against 2 atmospheres? So if I keep inflating the balloon, the walls are going to move, are going to be the ones with the lowest stress. And in this case, that's going to be, as I was saying in this example, south and north. And it's exactly the same here in the subsurface. The fracture is going to always open up, pushing against the wall, if we can think in a wall, on a fracture wall, with the lowest total stress. And in this case, that wall of lowest total stress is the minimum horizontal stress. And sometimes it's a little bit challenging to look at because some people tend to say the fracture propagates in this case in direction east-west. That's partially right, but it's also propagating in upwards and downwards. So that's something true, but it's not revealing everything about the fracture. A better way to understand how the fracture propagates is to think about in which plane the fracture is doing work against to. So in this case, the fracture is opening perpendicular to the minimum principal stress and doing work against that direction, and it's opening, as I was saying before, perpendicular to the minimum principal stress. So in general, always the fracture is going to open up perpendicular to the minimum principal stress. In this particular case, that's a horizontal stress, as we were seeing before in the case of a seal, a magmatic seal, that could be against the vertical stress. And that will depend on the conditions in situ. And if we go now to the map that we were seeing before, here you can see everywhere in the US what would be the expected orientation of hydraulic fractures in a particular place. And you see that it's not going to be the same in Texas as in Colorado, or wait a minute, or we're here in Oklahoma. It looks pretty straightforward. All the stress is going in east-west direction, the maximum stress, but it's going to change from place to place. And if you go to work somewhere else, I don't know, in Russia, in Argentina, wherever, those conditions are going to be very likely different. Okay. There's one more thing I want to show. Yes?
As you start creating the fractures, does the minimum stress increase, or does it always stay constant?
The far field stress is going to be more or less the same, but you may start to stress more the rock near the fracture, so locally that's going to increase. We're going to see that later on when we get to hydraulic fractures. That's something which is called stress shadow. It's an additional stress caused by the presence of the fracture. Okay, so I have one animation example here to see what is the effect of a deformation, a horizontal deformation on these stresses, and how we can go from something which is normal stress regime to strike slip and to horizontal. So let me run this quickly. I hope it works. This is an interactive Jupyter notebook. Are you guys familiar with Jupyter notebooks? So are these files that you can write and use Python code and combine it with text, and you can also do mathematical operations in it, print it as a PDF or whatever you want. They're quite useful, and it's just building up. It's so we can use it in this web page. Let's wait a little bit. Okay, while that continues, just let me see if I forget anything over here. Okay. Come back to this. No, not yet. Okay, so we're going to see a lot of this, but just as an example, here you can see if you wanted to do multiple stage hydraulic fracturing, you cannot see almost anything, right? Let's see over there. No, okay, no, this is not good. I'll change this plot. I'll do it now on the computer so you can see a little bit better. But this is just showing in which direction you may want to drill a wellbore to have multi-stage hydraulic fracturing. All right, what's going on here? Okay, still building. And this is one example, instead of in the Permian Basin, in the Barnett Shale. But it is the same thing. The direction of your wellbores is going to depend on what is the direction of the minimum principal stress. So in general, normal faulting or strike slip, you want the orientation of these wellbores to be aligned with the direction of the minimum principal stress. Any question? For the homework, we're not going to do much now about horizontal stress because one of our main objectives is to calculate and predict how the horizontal stress varies with depth. But we don't have the tools to do that right now. And it's going to take a little bit more of time for us to learn about that. For example, you can see in the code here I have a Young modulus, I have a Poisson ratio, and a few more variables that we're going to learn starting on Thursday about how we can use them to predict these stresses. But just for now, let me run this. Oh, I think this changed. All right, so here you have an example in which we see a profile of vertical stress and horizontal stresses with depth. We're going to see later on that for real rocks we have a Poisson ratio which is part of the solid, which is going to give us a horizontal stress which is higher than the pore pressure. And if I start pushing sideways, for example in direction 1-1, the stress in direction 1-1, which in this case is the green one, is going to be larger. If I keep on pushing in that direction, that stress may go a little bit larger. So let me come over here. What is that state of stress regime? according to what we just learned? Normal, right? Because the maximum stress is vertical and the minimum is horizontal, intermediate is also horizontal. If I keep on pushing direction 1, 1, now I get into another condition in which what stress regime do we have right now? Strike slip. And if now I not only push in one direction, but I push in two directions, I may be in a condition in which now both horizontal stresses are larger than the vertical stress, and now this is a reverse faulting stress regime. All right, guys, I think that's it for today. And on Thursday, we'll start talking about, we're done with this chapter. We'll start talking about linear elasticity and continuum mechanics. Just a reminder, remember that not this week, but next week on Wednesday, we have the laboratory, okay? So you do have to attend that one. That one is mandatory. So not this week, next week. So I'll send you a reminder Thursday, Friday, but next week we have the first laboratory. Yes? I'm pretty sure it was the week of February 10th, so that's going to be next week, right? Yeah. All right. Okay. See you guys. Have a good day.